Hey guys, welcome back to another video. This is a new series, and in this series we're going to be talking about electric fields. So the first topic in this video that we're going to be covering is Coulomb's law. So what is Coulomb's law and what is it talking about? Is it a formula and all that? So we're going to be covering all of that in this video, and it's going to comprise of the formula, the law itself, and how it relates to charges, right? Okay, so the basic few things that we need to understand is when charges interact, let's say about these two charges. What is this? Okay, so these two charges, right? Positive charge, a negative charge, right? If you put these two charges in each other's vicinity, what's going to happen? They're going to be attracted to each other. Agreed? Great. So when these two charges are kept together, they feel a sort of attraction. So they're feeling a pull, right? They're feeling a tug. Now, this pull, this tug, this is a force. Pulling is a force, right? So these two charges are experiencing a force towards each other since they are opposite charges. And these are the things we are already familiar with. Great. So if these two charges are experiencing a force, how do we calculate that force? And how does it affect other variables? And how do we get to other calculations using this force? And to know that, to know how we figure out the force and how the force affects other variables, we need to understand Coulomb's law. And it is the very basic part of electric fields. Why? Because anytime you put a charge, be it isolated or in the presence of another charge, they are going to have an electric field. An electric field. For negative charges, understand that the fields are towards the charge, and understand that for a positive charge, the fields are outwards. Why? We're going to be talking about that as well. So since these fields exist, what is the meaning of this field? This field is basically telling you which direction the force will be exerted. So if you bring another positive charge over here, this is going to be repelled by this positive charge. So the electric field is outward. The electric field is outward. This is feeling a force outwards. This positive charge, let's say Q2, is feeling a force outwards. That is why we need to understand field lines. Field lines is basically telling you the direction at which the force is acting. The direction at which the force is acting. And the field lines belong to what? Which one? This positive charge. So when this Q2 is introduced in the vicinity of this blue positive charge, it feels a force outwards. That is the meaning of field lines, right? This is giving you the direction where the force is being exerted. Now, this force that is being exerted, we can calculate it. We can calculate it using Coulomb's law. Okay. So, firstly, we're going to be understanding a few things. I've written a few points, so let's go through it. Okay, so for the 2 points, let's say Q1, right, and Q2, if they have the same or different sign, each will feel the same force as the other. What does this mean? What on earth does that mean? So, we have a charge Q1, let's say, and Q1, let's say both are positive charges, Q1 and Q2, both are positive charges, and none of those are equal. Q1 is not equal to Q2. Let's just assume that. Okay, so if Q1 is not equal to Q2, let's say this is 5 coulombs and this is 10 coulombs, both are positive. What's going to happen is both of these charges are going to face the same force. So what will happen in your imagination if we bring two positive charges together? As we've seen over here, they're going to be repelled away from each other. Great. So if they're going to be repelled away from each other, what is the force? What is the amount of force? Let's consider it X. Let's consider the force to be X newtons. This Q1 will feel it leftwards, and the Q2 will feel X Newton rightwards. So what's happening is, what the main point of telling or giving you this example is, mind you, the force, even though both charges are different, the force they experience is the same. The force they experience, even though the charges are different, are going to be same. Even if you bring out 5 coulombs of charge and 1,000,000 coulombs of charge, both will feel the same force, be it towards each other, be it away from each other. So it doesn't matter if you bring two different values of charge, same values of charge, opposite charges, same charges, doesn't matter. The force felt is always going to be equal. Is always going to be equal. Great. So if you get that, that is the fundamental idea of this, and that basically relates to the Newton's third law, action and pair forces. If you exert a force in this direction, there's going to be a force in the opposite direction as well. So it's basically that, and it's going to be equal, right? So Newton's third law says or states that every force has an equal and opposite reaction force. So minding that, even in this case, if you're exerting a force in this direction, you're going to feel a force in the opposite direction as well, and both of those are going to be equal. Great. So that is the first point. Done. What is the next point? Right, so if Q1 feels 5 Newton of force, Q2 will feel 5 Newton of force as well, right? Even if they have different charges. Good. Okay, next point. If both have same signs, they repel. If both are different, they're going to attract. I'm pretty sure you already know that. So next point. Both point particles or point charges need to have a charge for any of them to feel a force. So if Q1 has 5 coulombs and Q2 has 0 coulombs, then none feels a force. Very simple. Why? Because if this Q2 does not have a charge at all, what is this charge interacting with? This charge is interacting with nothing. So let's say you have a magnet, right? And you have a non-magnetic material. So you have a magnet and a non-magnetic material. Will this magnet interact with this non-magnetic material? No, it won't, because they don't. It doesn't have magnetic field lines for this to interact with this. So similarly for charges, if one has electric field lines and this does not, what is it going to interact with, and how will they feel a force? Very simple. So if either of the charge don't have a charge on it, or it doesn't have an electric field, it's not going to feel a force. None of the particles are going to feel a force. Okay. So that's the third point. Those are the basic few points we want to establish before we start talking about Coulomb's law, right? So hopefully you now understand how charges interact and how there are forces being exerted and in what manner they're being exerted. Great. So if you understand the basic things, let's move on to the Coulomb's law, the main topic of this video. So right, if we take two charges, Q1 and Q2, obviously the force, as we have already mentioned and stated, F1 and F2 on each other are going to be equal. So if both of these charges interact with each other, the F1 towards this, let's say both are probably opposite charges, because otherwise they're not going to be attracted towards each other. So if both are opposite charges, F1 is going to be equal to F2. They're being attracted towards each other, and that attracting force, pulling force is going to be the same. Okay, great. So we have established that. Now, the second part of Coulomb's law is that the force is proportional. Yeah, so the force is proportional to the product of both the charges. Okay, so what is the Coulomb's law telling you? the force is proportional to the product of this charge and this charge. So if you multiply Q1 and Q2, it is always going to be proportional to the force. So if you, let's assume you keep the Q1 same and you increase Q2, the charge on Q2, particle 2, the force is going to increase as well. The force is going to increase as well. So let's forget about Q2 and increase the charge on Q1, particle 1. What's going to happen? The force that both experience are going to increase as well. So the main idea is force is proportional to the product of Q1 and Q2. Whatever the product is, if you increase that value, F, the force will increase as well. Good. So, right. Okay. Now, the other variable, the other part of this law is force is inversely proportional to the separation of the charges. This is the distance between the point charges. Distance between the point charges. Okay, so let's understand this. What are point charges? You probably already know this from gravitational fields. So anyways, I'll still talk about it. For these, spherical charges, you can assume the charge to be concentrated at the center. I probably will talk about it again later on in different videos. But yeah, so you can assume these spherical charges to be point charges. Why can you assume that? Because if you draw the field lines, let's say if this is the positive charge, the field lines are outwards. They are outwards like this. And notice, if you look at the charge, you're going to assume these arrows are going to meet at the center. These arrows, these radial arrows, are going to meet at the center. This is what it seems like if you look at it. So that is why you can assume these are acting like point charges, and for them to be point charges, they need to be uniform as well, so that they meet at a single point, right? At least you can assume that, right? Okay, so we can make that assumption that these are point charges since the arrows seem to meet at a center point. The fields seem to meet at a center point, and it feels like from this point that the field lines are being, escaping. Okay, so where were we? Right, so the separation from this point charge right at the middle, you're going to draw a line. Let's draw a line right at the middle. So if you now, this is R, again right at the middle, this entire part is your R. The separation between the point charges, that is your separation of the charges, right? So notice that force is proportional to the square of the separation, inverse square of the separation, right? So if you increase the, let's say, separation, what's going to happen is the force is going to decrease. Right? So that's the third part, I guess, right? So if you combine all of these are basically, I'm just stating the parts of the Coulomb's law, and I'll explain why all of these are happening later on again if needed. So yeah, that's the first part. F1 is equals to F2, and second part is force is proportional to the product of both the charges, and force is inversely proportional to the square of separation. Okay, so if you combine all of that, F is inversely proportional to R square and F is directly proportional to the product of both the charges, you get this proportionality. Great. So where do you go from here? Now, to build an equation, what do you do? To remove this proportionality, what you do is you remove it and include a equals to sign and bring a constant. That is K. Constant K. Okay, so what is this constant K now? So through various experimentation and trial and error, our good old friends from science have figured out that the constant k is actually 1 by 4 pi epsilon naught. How did they come to this conclusion? You don't need to know. But it's basically they found out this interesting variable that you might be curious about. And I'll be explaining what this E naught is. This is called permittivity, and this is a part of the K constant. And this entire thing is for your syllabus, it's going to be remaining the same. We're going to consider the permittivity of a vacuum. What is all that? I know it sounds like jibber jabber, but I'm going to explain all of that. So this entire thing is the constant again, and you're pretty familiar with 1 by 4 pi, I guess. You should be. And this is the strange part. What is epsilon naught? Permittivity, right? Okay, so epsilon naught is basically, if I go to the next part, oh, by the way, so the value is this 8.9 10 to the power 9 of this. So you can directly plug in this over here while calculation. I don't know if this is given. The epsilon naught value might be given, or the entire value might be. I'm not really sure. You can check the data booklet. So yeah, the derivation of this is not needed, and the value, if you know this value, you can directly plug this into over here. And if not, if you want to write the full form of the equation, you write it as q1 q2 by 4 pi epsilon naught r squared. This you have to plug in from the data booklet in that case, if you want to use this entire equation. And if you remember this, you can just plug this in instead of k to calculate the force. Okay, so coming back to epsilon naught, what is epsilon naught? E naught is the permittivity of free space or vacuum permittivity. E naught. Whenever you see E naught, that is basically talking about vacuum or free space, people call it. And it's not going to be air, to be honest, because it's going to vary a bit for the medium to be air, and the values are going to be different. So E naught is basically talking about vacuums. Okay. So for vacuums, they have figured out the permittivity is actually 8.854 into 10 to the power minus 12 farads per meter. Okay, so what is permittivity again? It is a property of any material that measures the opposition it offers against electric field. What does this mean? So basically, in any field, for electric fields to exist, there might be or there will be some amount of resistance to it. So you can look at permittivity in a sense of amount of resistance against the electric field. This is one way of looking at it. And the other way to look at it is, this is a bit, I guess, advanced and unnecessary to understand. So this is talking about another way where if you look at it as a tendency of a material's atomic charge to distort when the material is placed in an electric field. So if, be it any medium, if you're placing a point charge in that specific medium, be it air, be it water, be it anything, the atoms of the medium, the shells, the field around it is going to distort in a specific way, and permittivity is a measure of that distortion that is affecting at the end of the day your electric field. So you don't need to know all of that. You just need to know E naught is a constant that we consider for figuring out the force acting on the charges. So you just plug E naught into the equation and find out the force. You don't need to know the derivation. You don't need to know what it means. You're going to learn about it later on. I'm pretty sure you're going to learn about it at uni if you do take physics, right? So as I've already mentioned, force is the product of the both charges divided by 4 pi epsilon naught r squared. That is your equation for the force or the Coulomb's law. Okay. So if I define Coulomb's law, it's going to be the force between 2-point charges that is directly proportional to the product of their charges and inversely proportional to the square of their separation. Now, if I draw the graph between force and r, it's going to be a typical y is equals to 1 by x square curve. So if your 1 by x curve was, let's say, y is equals to 1 by x was, let's say, something like this, it's going to be more steep. That's the only difference. And you're going to notice it when you judge the curves between the electric potential and the force curves. So in one, there is r square as the variable. In the other, you have r as the variable. And we're going to talk about it, don't worry. So in the case of when force is proportional to r square, this is going to be much more steep. That's the only difference. And the all inversely proportional curves look like this. It's like asymptotic on these two ends, right? So yeah, this is basically the graph for the relationship between force and the separation between the charges. Okay, that's about it for Coulomb's law, and I'll try to talk about it in more details in the next video.